This terminal illustrates the core conflict. To build a real-time collaborative document editor like Google Docs, you have to manage what happens when two users type over each other in the exact same location. Now consider the scale. You need to support 100 million active users who expect millisecond response times and strict access controls, all hitting the same infrastructure simultaneously. Traditional relational databases handle concurrency through row locking. If one person edits a specific row of data, the database locks it down so no other process can overwrite the work until the transaction is complete. Locking a document every time a user presses a key would prevent anyone else from typing. The collaborative experience would stall immediately. This creates a paradox. We must allow multiple asynchronous users to edit the exact same string of text at the exact same time without losing anyone's data. To see how systems at this scale actually function, we are going to design this architecture from the inside out, starting with the algorithmic bottleneck. At this density of traffic, the engineering challenge is concentrated entirely on state synchronization. This diagram illustrates a classic race condition. In a character array spelling hello, user 1 prepares an insert operation at index 5. User 2 prepares a delete operation at index 4. If a standard server processes these commands out of order due to network latency, the indices no longer match the current text. The array corrupts. We solve this using operational transformation, or OT. We place an OT server node between the users and the data to act as a mathematical arbiter. The core logic of OT is that the server never accepts raw text. It only accepts mathematical operations. When user A sends an insertion command, the OT node intercepts it and calculates the new total length of the string. While that happens, user B's concurrent deletion arrives. The engine recognizes that user A just shifted the array. It transforms user B's operation data in midair, shifting its target index by 1 to account for the new character. The server then fans out those transformed operations to all connected clients. Both users see the exact same synchronized text. Clients also run this logic locally. They resolve their own pending keystrokes against incoming server operations before rendering them to the screen. This setup relies on eventual consistency. While a local client might show a brief mismatch, the mathematical transformations ensure every user's screen aligns within milliseconds. By mathematically shifting indices on the fly, OT removes the need for database locks, making sub-second collaboration possible. With the algorithm solving the race condition, we have to address the network. We need a way to transmit thousands of these operations per second with minimal overhead. Standard HTTP polling is too slow and resource-heavy for real-time keystrokes, as the repeated request-response cycles create significant latency. This diagram shows the required protocol, WebSockets. WebSockets establish a continuous, bidirectional connection to our document editing service, allowing for immediate data pushes. Speed is only half the battle. We also have to persist this data without incurring massive cloud storage costs. Saving a full document snapshot to a database after every keystroke generates redundant text payloads. At scale, this would quickly overwhelm the storage layer. The solution is event sourcing. Instead of saving the entire document, we save an append-only timeline of the operations themselves, similar to a Git commit history. Because this system generates a relentless stream of tiny, discrete writes, a write-heavy NoSQL database like Cassandra or DynamoDB is the logical infrastructure choice for this log. This same logic integrates features like text formatting and user comments. Formatting is not saved as HTML embedded in the text. It is stored as a separate metadata operation tied to specific index ranges on the timeline. The document on the screen is a client-side render. The source of truth on the server is just a timeline of mathematical operations. We have a highly optimized engine for the editing state. Now we have to manage the static elements of the document, such as titles, the creation dates, and user permissions. In distributed systems, high-frequency volatile state is decoupled from low-frequency static data. We introduce a separate document creation service with its own isolated NoSQL metadata database. This service handles the initial setup, assigning the document ID and basic metadata before any editing begins. This decoupling also accommodates large media. A heavy image payload bypasses the operation timeline entirely. It uploads to an S3 blob storage bucket, which returns a lightweight URL to the metadata database. Finally, the system requires a way to enforce role-based access control to determine who can edit, comment, or view. We secure the entry point by placing an API gateway and an identity access management service at the front of the architecture perimeter. When a client connects, the API gateway validates their JWT token against the IAM service. Once the user is verified as an editor, the gateway routes them to the WebSocket editing service. This perimeter protects the concurrency engine from unauthorized access and large media payloads, allowing the core timeline to scale cleanly. Tracing the lifecycle of a single keystroke shows the entire system in motion. A keystroke hits the API gateway, passes via WebSock to the editing service, transforms through the OT engine, appends to the NoSQL log, and fans out to the second user screen. Solving the state synchronization bottleneck required the specific logic of the operational transformation algorithm. Managing storage costs drove the implementation of event sourcing on NoSQL infrastructure, and the need for system stability required decoupling the identity and media storage from the core editing microservices. To support 100 million users, the architecture treats the document as an ordered timeline of mathematical operations rather than a static digital file. Tracing the lifecycle of a single keystroke shows the entire system in motion. A keystroke hits the API gateway, passes via WebSocket to the editing service, transforms through the OT engine, appends to the NoSQL log, and fans out to the second user's screen. Solving the state synchronization bottleneck required the specific logic of the operational transformation algorithm. Managing storage costs drove the implementation of event sourcing on NoSQL infrastructure. System stability required decoupling identity and media storage from the core editing microservices. To support 100 million users, the architecture treats the document as an ordered timeline of mathematical operations rather than a static digital file.